Hello, here's the last day of new stuff for the logs unit. All right, I promised to go over a couple questions on last night's homework first. So if you want to grab that, or if you did fine on it and want to skip past this part, that's fine too. But the first one I said I'd go over is number 10. Some people exponentiated by 2 right away, but remember there's that trick. This exponent, there's no way I want to do 5x plus 7 to the 19th. So if I bring that 19 out front and say 19 log base 2 of 5x plus 7 equals 57, then I'll be able to solve this a lot easier if I divide by 19. And 57 divided by 19 actually is a nice number. It's not one we're used to. Oops, there's no log in. Log base 2 of 5x plus 7 equals 3. And then if I exponentiate by 2, I'd have 5x plus 7 equals 8, 2 cubed. 5x equals 1 when you subtract the 7, and x equals 1/5, which would work because 5 times 1/5 is 1, plus 7 is positive. So there's your answer. All right, then over on the back, most people got number 7, but again, Drew said that that equation can be solved because he expanded and got that crazy number and realized that he cannot solve the resulting equation. Is he correct? Some of you did y1, y2 calc intersect, which is great. I never even thought of that, and saw that he got x equals 3. Okay, so that would be a good way to do it. I think he means he can't solve it by algebraic methods. So what could he have done up here that would have avoided having to expand this all out? All right, same thing as the last time. Bring the 4 out front. So 4 log base 2 of x plus 1 equals 8. Then divide by 4. So log base 2 of x plus 1 equals 2. Exponentiate by 2. And you have x plus 1 equals 2 squared. X plus 1 equals 4. So subtract, and there's the x equals 3. So just remember that exponent trick, because bringing that out front and dealing with it that way can save yourself time instead of expanding out. All right, I wanted to talk about number 10, the log equation. So determine the domain of that log and express your answer in interval notation. Again, domain keeps giving people trouble. If you see a log, you know, in this yesterday's video, we always rejected things that made logs negative or 0, because the domain, the stuff inside it, x plus 4, is greater than 0. So x has to be greater than -4, which means my domain is -4 to infinity. Now remember, that also tells you the asymptote. Since -4 is a parenthesis, that means if I go to -4, that is the spot that's going to have the asymptote. So make sure you draw that asymptote in. You need that. Because some of you still did what I said not to do on the video yesterday. You just did math, log base 3 of x plus 4 from standard, and you kind of just drew a graph that looks like it started in the middle of the page and went off. And that's not exactly true. That's the basic shape, but again, look at the table. Look for nice numbers. -1, 1 is a point we'd have to use. So if I do -1, 1, there's a point. What else? If I go this way, -3, 0, and then all the errors start, because starting at -4, there's our asymptote. So -3, 0, we can plot that point. And then as I go to the right, let's try to find at least one more good point. 5, 2. 1, 2, 3, 4, 5, 1, 2, like that. Okay, connect the dots. That's not good enough. You can't draw it like that. You have to show it approaching the asymptote down there. Okay, so make sure your graph looks something like that. All right, and then the last one, the word problem, always gives some people some issues too. It's not as bad as you think. Students participating in a psychological exam attended several lectures on a subject and were given an exam every month for a year. Students were retested to see how much of the material they remembered. The average scores for the group are given by the human memory model, which is modeled by this formula, where T is the time in months. what was the average score on the exam when t equals 0? So for part A, all you really have to do is plug in 0 for t. So f of 0 is 75 minus 6 ln of 0 plus 1, or 1. And you can type that into the calculator, but what did I always say log of anything of 1 is? The exponent, whatever the base is, the base raised to what exponent is going to give you 1? 0. So that's zeroed out, and I have 75. Part B is basically the same. What's the average score at the end of 2 months and at the end of 6 months? We're just looking for f of 2. Because t is in months, so t is the months. That's how I know to plug that in. So 75 minus 6 ln of 2 plus 1, or 3. And at the end of 6 months would be 75 minus 6 ln of 6 plus 1, or 7. And that's just straight calculator. Remember, ln is an easy thing to type into the calculator. I can just do 75 minus 6 ln of 3, which goes about 68% after 2 months. And 75 minus 6 ln of 7, it's about 63% after 6 months. So 68%, 63%. And then finally part C, determine the time to the nearest whole month when the average score was 60. So now I'm looking for the average score being 60%. That goes in the left-hand side. That's what the function's describing. We're solving for the month. And I saw a lot of you did y1, y2 calc intersect, which is totally fine. I didn't say it had to be algebraically. Let me show you. Really, it's pretty easy to solve this algebraically. You have to isolate the log, so subtract the 75. You get negative 15 equals negative 6 ln of t plus 1. Divide by negative 6, which isn't an awful number, I don't think. Negative 15 divided by negative 6 is just 2.5. 2.5 equals ln of t plus 1. Now, how do you get rid of an ln? You exponentiate by e, like that, because ln is log base e. So that goes away. We have e to the 2.5 equals t plus 1. To just subtract the 1, e to the 2.5 minus 1 equals t, and you'll get your answer, e to the 2.1, or 2.5, sorry, minus 1, and you get 11.1. And I said to the nearest whole month, so that's why it was about 11 months. All right, so hopefully that cleared up any homework questions you had. Now let's move on to today's stuff. Start with the warm-up. Now the warm-up is in your packet. If you look through probably before the next page of notes, you'll see this. Take a few minutes and try to just evaluate 1 to 10. You can type them into the calculator. So like number 1, you'd be typing in log of 10 to the 4th, log 10 to the 4th, and see what you get. Four. So everything on the right side is easy to type into the calculator because it's just log or ln. On the right side, see if once you do the left side, you see the pattern if you don't know it already. Then see if you can do the right side without typing into the calculator. Okay, so pause the video, take a couple minutes, and do this. Okay, if you are watching this, hopefully you've had a chance to try this on your own. Let's go through it. Going down the column here, if I do 10 raised to the log 100, what did you get? 100. And if you did ln of e to the 7th, what did you get? ln of e raised to the 7th. 7. E to the ln of 5. E raised to the ln of 5. 5. 10 raised to the log of pi. 10 raised to the log of pi. 3.14159, that's pi. So what's happening? And just something that you've seen a bunch. Log is really log base what? Log base 10. So log base 10 of 10 to the 4th, those are going to cancel, and I get 4. The other side is also true. If I exponentiate log by 10, 10 raised to the log base 10, those also cancel. ln and e, same idea. ln is log base e, which incidentally, that's an L, not an I. Some of you are using IN. ln and e cancel each other out. Same with exponentiating by e and ln. 10 raised to the log base 10 again. We've seen that. So what are all these going to equal? Sorry, the numbers are kind of screwed up. 6 to the log base 6 of 40 equals 40. Log base 4 of 4 to the x equals x. 4 raised to the log base 4, you're just going to get whatever's in the exponent, even if it's x squared plus 1. Log base 7 of 7 to the w, w. And 7 to the log base 7 of 1/2 would be 1/2. So this is just reminding you that that whole idea of the inverse operation. If you have b raised to the log base b of anything, x, you're just going to get x. And if you have log base b of b raised to the x, you're just going to get x. And that whole idea goes back to the idea is because logs and exponentials are inverses. And I go back to that because that is the main idea of this whole unit. That is the purpose of the unit. To know how to get rid of a log. If you want to get rid of a log, you exponentiate. If you want to get rid of the base of an exponential equation, you take the log of that base. You never divide by the base. And in fact of the day, there are 18 different animals in the Animal Cracker Zoo. Now you know, if you've been following the news in the last couple of years, we can't even lock up the animals anymore in the fake zoo. Anyways, let's go on to today's notes. New exponential equations. So these are exponential applications. I keep calling them equations. These are the same equations we did in the last unit. The only difference is now that we know logs, we can solve everything algebraically. We don't need to do that y1, y2 calc intersect. So the 3 formulas that we used in the last unit are the same 3 we're going to do today. We have A equals P times 1 plus or minus R to the T power. We have A equals P times 1 plus R over N to the NT power. And we have A equals PERT, PE to the RT. Then we had a 4th one in the last unit. Anyone remember what it is? The half-life one. And you can absolutely solve half-life equations with logs as well. I'm just not going to talk about them today. All right. So do you remember what the key word for this middle one was? Compounded. It's compounded quarterly or monthly or anything like that. We use that formula. What about for PERT? What was our key word for that? Right, continuously. And continuously trumps everything. So if it says compounded continuously, you use PERT. The other one was just your general exponential equation. If you don't see the word compounded, don't see the word continuously. That's just if you increase or decrease by a constant rate. That's what makes it exponential. What was P in all of these equations? P was the initial amount. What was R? R was the rate. That's a decimal. So usually they'll give it to you in some sort of percent, but remember you gotta change it into a decimal. What was T? T was usually some unit of time. And then this middle formula had this extra N. What was n in that middle formula? It was the number of compoundings per year. So if it was compounded quarterly, it was 4. If it was compounded monthly, it was 12, etc. Weekly was 52, because everyone knows there's 52 weeks in a year, right? Okay, so a lot of the questions you're going to see are not any different than the ones we did in the last unit. We're just not going to solve them graphically anymore. Everything's going to be algebraic. Okay, number 1, in 2015, the population of a city was 43,600. Suppose the population increased at a rate of 2% per year. Develop an equation that represents the population of the city t years since 2015. Using your equation, determine what the population of the city will be in 2020 and in 2025. Finally, use your equation to determine in what year the population will reach 60,000. All right, so we kind of got 3 parts here, all smushed into this big paragraph. First thing we're supposed to do is develop an equation that represents the population of the city. So which of these 3 do you think we're going to use? There's no words about compounded, there's no words about continuously, so it's just the first one. So it's going to be A equals P times 1. Is it plus or minus? The population is increasing, so it's plus R to the T power. All right, so the initial amount was 43,000. So A equals 43,600. R is 2%, so we're going to write that as 0.02. 1 plus 0.02 raised to the T. And we can combine that, make that look a little bit nicer. A equals 43,600 times 1.02 to the T. And notice there's no crazy variables they want us to use, so there's the first part. So just to put it into perspective, we've got an exponential equation. Where would your y-intercept be? 43,600. And it's increasing at 2% per year, so the population is going to go something like that. Okay, using your equation, determine what the population of the city will be in 2025. Or 2020 first. Well, 2020, what would I plug in? It's definitely a time, so it's going to be t. And since it's all based off of years since 2015, that's year 0. This would be when t is 5. Okay, so I would just say A equals 43,600 times 1.02 to the 5th. We go to our calculator. $43,600 times 1.02 raised to the 5th, and I get 48,137.9, so we'll just round it up, 48,138 people. All right, so similar idea, if I wanted to do 2025, what would I do? Right, I just plug in t equals 10, because that's 10 years since 2015. So 43,600 times 1.02 to the 10th. 43,600 times 1.02 raised to the 10th. And I get 53,148 people. Okay, nothing crazy yet. Finally, use your equation to determine in what year the population will reach 60,000. Okay, so for this last part, I want in what year. So I want a t value, and when do I want it? I want it when the amount was 60,000. So this is where I plug 60,000 in on the left side, equals 43,600 times 1.02 to the t. Now this is where in the last unit we did y1, y2, calc intersect. All of you got really good with that, got your answer, no issues. What should you do here? I want to do it algebraically today. So I don't want to do y1, y2. We know how to solve this now though. What do you think you would do first? I've got to get t alone, but I've got to isolate the thing that the t is on. The t is on the 1.02 right now. So divide by 43,600. Get that to cancel. And then let's see what the calculator gives us. 60,000 divided by 43,600. And I get crazy decimal. Let's see if a fraction is better. 159 over 109. It's better than using that big decimal. All right, now what could you do? I gotta get to this t, so I hope no one's even considering dividing by 1.02. If you were, shame on yourself. What's the whole purpose of this unit? Logs, right. If you have a new calculator, I would just take log base 1.02. If you have an old calculator, I would just do the log of both sides. And we'll do both ways. For this one, I'll assume you have a new calculator. So let's say take the log base 1.02 of both sides. Log base 1.02 of this number equals log base 1.02 of 1.02 to the t. That cancels. Go to your calculator, math, alpha, math. Log base 1.02 of 159 divided by 109. 19.06, something like that. Did I do that right? Oh, sorry, not closer to that. That was 150 over 109. Sorry, stop groaning. So that should have been 150 on all these. Try that one more time. Log base 1.02 of 150 over 109. 16.123. It wants to know in what year. So if it's 16.123 years since 2015, in what year is that? It would be in early 2031 if you add 16 to 2015. All right, any questions? Really nothing new today. It's all review of these applications, just solving them with logs. Okay, number 2. Alex purchases a new car for $30,000, which depreciates at a rate of 15.5% each year. According to the model, will the car ever have a value of 0? Explain. Well, let's make a model first. Which of those 3 equations up at the top are we using? First one again, because there's no compounded and there's no continuously. But this time it's depreciating, so what's that tell us? That it's decreasing. So it's a equals p times 1 minus r to the t. So the equation would be a equals, what goes first? Initial amount of the car, 30,000, times 1 minus 15.5%, that's 0.155 to the t. Try to clean that up a little bit. 1 minus 0.155, 0.845. So a equals 30,000 times 0.845 to the t. Will the car ever have a value of 0? Well, there's a couple ways to answer this. We could think about it graphically. So graphically, this is an exponential equation. Oops, it's decreasing. So it's starting up here and going down. Do you think it's ever going to reach 0? Well, remember, exponentials have a horizontal asymptote at 0. And this isn't shifted up or down at all, so it's never actually going to reach 0. So graphically, no, because it won't reach 0. Let's see what happens algebraically. If I put 0 in the left-hand side, what would you do to solve it? You would divide by 30,000. We get 0 equals 0.845 to the t. Then what? You could take log base 0.845 of 0 equals log base 0.845 of 0.845 to the t. And hopefully you already know what's going to happen when I do this. Log base 0.845 of 0, it is error domain. Why? Because you can't take a log of 0, right? Error can't have log of 0. So no, car never has a value of 0. Good? Okay. Part B. According to this model, when will the car's value be half of its original value? Well, what is half of the original value? 15,000. We want when. So I want the t variable again, and I want it when the amount is half of the initial, so 15,000. So I'm just going to do 15,000 equals 30,000 times 0.845 to the t. Then what? Divide by 30,000. We always have to divide by that piece out front because that's not being raised to the exponent. That's going to be 1/2 or 0.5 equals 0.845 to the t. Then what? Log base 0.8.5, good. Just for those of you who can't do that log base key, I would probably just say take the log of both sides at this point. Remember, there's different ways to solve these. So if you just take the log, this won't cancel, but what does it let you do? It lets you bring the t out front. So those of you that can't use the log base key, take the log, bring the t out front, so t times log of 0.845. Then what? You want to get t alone, so divide by log of 0.845. And then go to your calculator, type in log of 0.5 divided by log of 0.845, and I get 4.115 equals t. What did it say to round to? It didn't, so we'll say about 4 years. It's going to be worth half of its value. Okay, so again, if you have the log base key, just taking log base 0.8.5 probably would have been the way I would have gone, but I wanted to give you this other option for when you have a weird base or if you don't have that key. All right, over to the back. Grandma Laley, she was great, has $20,000 to invest and wants to save $32,000 to help her favorite grandson purchase a new house. I wonder who that is. She expects her investment to earn an average of 6% a year, compounded quarterly. In how many years to the nearest year will she reach her goal? Okay, what formula should Grandma Laley use? Compounded quarterly, so this one. So we're going to have A equals P times 1 plus R over N to the NT. Now, even though it doesn't tell us to make a formula, let's write it before we figure out what we're plugging in. What do I know? I know 20,000 is P because that's the amount that she's investing. She wants to save 32,000, okay. The investment is going to earn a rate of 6% a year, so what's R going to be? 0.06. And compounded quarterly, what's compounded quarterly tell us? Well, if we're using this formula, it tells us that N is 4. So my formula is going to be A equals 20,000. 1 plus 0.06 over 4 raised to the 4t. Now this looks kind of ugly in here. We can see if it comes out to be a nice number. Sometimes it will. That's not too bad, 1.015. So I'd probably just use that in here. A equals 20,000. 1.015 to the 4t. But if for some reason this came out to be some crazy decimal, we can't round early. So if this was a crazy decimal, I would have just left it like this and dealt with it in this form. Okay, how many years will she reach her goal? So her goal is that 32,000. So if I want how many years, what variable do I want? I want time, t, and I want it when a is 32,000. So I'm just going to have 32,000 equals 20,000 times 1.015 to the 4t, and I got to solve it. So what's the first step? Divide by 20,000. Cancel. And we have 32,000 divided by 20,000, which is 1.6. Not bad. Oops. Then what? This is your log step, whether you just want to take the log of both sides and bring the 4t out front, or if you want to do the log base. We'll do the log base this time. Log base 1.015 of 1.6 equals log base 1.015 of 1.015 to the 4t. We know those are going to cancel. I'm just going to leave this as log base 1.015 of 1.6 for now, because I know it's going to be an ugly number, equals 4t, because then what do I still have to do? I have to divide by 4. So let's just type that all in one step. Log base 1.015 of 1.6 divided by 4. 7.89. So it's the nearest year. T is about equal to 8 years. All right, so I encourage you, if you don't have that log base key, to try doing this as well by taking the log of both sides and make sure you can get the right answer. All right, a couple more. Number 4, this year Eric deposits $3,000 in his new savings account that pays 5.8% annual interest compounded continuously. As soon as I read that, what do you know? PERT. How long will it take his savings to double in value? All right, let's make the equation. A equals what out front? Initial amount, so 3,000 times e to the 5.8% would be 0.058 t. I want to know how long, so again I want t. And when do I want it? No, I want it when his savings doubles, so when the amount is 6,000. So 6,000 equals 3,000 e to the 0.058 t. What's our first step? Still have to get rid of that number out front because the e is being raised to that power. So divide by 3,000. You're going to get 2 equals e to the 0.058 t. Now what should you do? We got to get rid of that e. Good, you should ln. So ln both sides. ln of 2 equals ln of e to the 0.058 t. Those cancel. So ln of 2 equals 0.058 t. Divide by 0.058. And I've got ln of 2 divided by 0.058. 11.95. So it doesn't tell us what to round, so we'll say about 12 years. Good? Okay, last one. And you might recognize this formula. It says Newton's law of cooling states that the temperature of an object T decreases exponentially as a function of time according to this crazy looking formula. In this formula, T sub 0 is the initial temperature of the object. T sub A is the temperature surrounding the object, and K is a constant. A corner coffee shop has an air temperature of 70 degrees and serves coffee at 206 degrees. This was the exact question that was on the Regents review last unit. If the customer determines that the coffee has a temperature of 78 degrees after 10 minutes, determine the value of K to the nearest thousandth. Okay. The Regents loves giving you crazy formulas to plug in. So let's see if I can figure out what would go where. T sub 0 is the initial temperature of the object. Any idea what that would be? Well, the object we're talking about is the coffee, and the coffee shop serves it at 206 degrees. That's the coffee's initial temperature. T sub A is the temperature surrounding the object. What's that going to be? 70, because the air temperature is 70 degrees. So 70 is T sub A. What else do I know? The coffee has a temperature of 78 degrees after 10 minutes. So that's the ending temperature. This is T, and this is the time. That's little t. And then I think I have everything I need to solve for K. So we can do 78 equals 70 plus 206 minus 70 times e to the negative k times 10. Actually, I don't think this was the last Regents review. I think this was on a homework in the last unit. All right, so let's clean up that. What's 206 minus 70? 136. So 78 equals 70 plus 136 e to the negative k times 10. And if I want to solve this algebraically, in the last unit, again, you did y1, y2, I've got to isolate the e, because that's what the exponent's on. So first I would subtract the 70. So we get 8 equals 136 e to the negative k times 10. Then what? Divide by 136. So what's that? 8 divided by 136. Crazy decimal. So let's just leave it as a fraction. Let's just say 8 over 136 equals e to the negative 10 times k, or k, negative k times 10. Now what? We gotta get rid of the e, so that's where we ln. So that cancels. And I have ln of 8 over 136 equals negative k times 10. Last step. I want to solve for k, so divide by negative 10. So ln of 8 over 136 divided by negative 10 will be k. Let's see what that is. ln of 8 over 136 divided by negative 10. And k is 0.283, said nearest thousandth, so that's 3 decimal places. Okay, last one. Coffee experts say coffee tastes best at a temperature of 140. If this is true, how long to the nearest tenth of a minute does it take the coffee to reach this temperature? So most of what we have is the same. Surrounding air is still 70. The serving temperature is still 206. It's just I want to know when. So I want what variable? I want time, so that's little t. And I want it specifically when what happens. With the actual temperature, the ending temperature, big T, is 140. So it's basically the same thing. I'm going to put 140 over here equals 70 plus, this isn't changing, so I'm just going to write 136. E to the negative, put the K value you just found in, 0.283 T. And then solving this is basically the same. What's my first step? Right, subtract 70. So if I subtract 70, I'll get 70 equals 136 e to the negative 0.283 t. Then what? Always got to isolate the exponential, so divide by 136. So 70 over 136 equals e to the negative 0.283t. Now what? This is the important step. I got to get rid of e, so I'm going to ln both sides. So ln of 70 over 136 equals negative 0.283t. Last step, divide. And plug it all in. ln of 70 over 136 divided by negative 0.283. And my answer is 2.346, rounded 2.35. 2.35 minutes. Actually, it says nearest tenth. So let's look at that again. Nearest tenth would be 2.3. 2.3 minutes. All right, there you have it. So now you know how to solve exponential applications algebraically. And that's usually what the Regents is going to ask you to do. Okay, so give the homework a shot. Let me know if you got any questions, and good luck.